Hello, on behalf of our investigative team, I would like to welcome you to this presentation on the application of Ecuadorian ferrotitaniferous sands in reinforcing epoxy composites. The contents that will be discussed in this presentation will be a brief introduction, a section about materials and methods, a section about results and discussion, and finally, some final remarks included in a conclusion section. In the field of polymer composites, epoxy resin is an extensively used thermoset that exhibits engineering properties thanks to its densely cross-linked chains and chemical structure. Besides, epoxy resin presents low density, lack of volatile curing byproducts, easy processing, and a hydrophilic nature. This resin is mainly used as an insulator coating adhesive and for advanced composites. Nevertheless, epoxy resins exhibit low Young's modulus compared to other thermosets like phenolic resins and unsaturated polyesters. Apart from this, they also exhibit a low impact strength. All these things limit their applications in many industrial fields. Low-cost ceramics are deemed as promising fillers in the field of polymer composites. Some micronic iron oxide-based minerals have attracted the attention of the scientific and industrial sectors due to their intrinsic magnetic properties and characteristic gamma and X-ray attenuation. Among them, naturally occurring black beach sands, also known as ferrotitaniferous sands, composed primarily of ilmenite, raise special interest. In South America, these sands are prevalent along the coastlines of various countries, and traditionally, this type of deposits have been mostly exploited with the purpose of obtaining titanium oxides. However, the low titanium oxide recovery rate is still insufficient to justify the mining process. In Ecuador, these sands can be localized primarily along its Pacific coast with an estimated commercial value of $24 per ton and have been conventionally used only as a cement clinker additive and agro-industrial fertilizer. Recently, these sands have been employed as a low-cost precursor for the synthesis of iron titanium oxide-based nanostructures via soft chemistry approaches. However, applications of Ecuadorian ferrotitaniferous sands without chemical treatments have still not been reported in the literature as far as we know. A previous study determined that these sands are an ilmenite hematite solid solution. As a matter of fact, solid solutions between ilmenite and hematite both display semiconducting and ferromagnetic behavior, resulting in a non-traditional magnetic semiconductor with conceivable spintronic and ionizing radiation barrier applications. Hence, this work is intended to evaluate the effects of ferrotitaniferous sands in reinforcing an epoxy resin through micro-indentation and dynamic mechanical analysis. This study is a framework for the exploration of the mechanical and thermal responses of the as-prepared composite as a valuable step towards expanding the application of the ferrotitaniferous sands in this research area. For this work, Ecuadorian ferrotitaniferous sands were collected from the Oceanal Beach located in Mompiche Esmeraldas. The collected sample was ball milled using conditions determined in a previous work, and the sand size was determined through dynamic light scattering analysis. As you can see in the SEM image, these sands present an irregular shape, so on average, the particle size is around 450 nanometers. The composites were obtained following the procedure shown in the following schematic. In a determined amount of epoxy resins, these sands were added. The sand contents used were 2, 4, and 6% in weight. Then, these sands were dispersed by sonication in an ice bath. Afterwards, the curing agent was added to the as-prepared dispersion and manually stirred during 5 minutes. The composites were shaped by casting in acrylic molds. Finally, the upper specimen surface was polished to improve the surface quality. The as-prepared composites were denoted as shown in the figure on the right. The control sample and composite specimens were tested through microindentation using the conditions shown on the screen. Both the elastic modulus and hardness of these composites and sample were computed employing the Oliver-Farr method. On the other hand, dynamic mechanical analysis were carried out to quantify the storage modulus, the loss modulus, the damping factor, and the glass transition temperature. These analyses were performed using the conditions shown on the screen. The results of the microindentation test are shown on the left, and using the Oliver-Farr method, the Young's modulus of the distinct as-prepared composites are shown on the right. It is observed that a maximum increase of 6% was obtained with the reinforcement mass percentage of 6%. These results are presented with the respective micromechanical models used, modified rule of mixture, and Halpin-Tsai models. Micromechanical models are used to predict the final characteristics obtained through a composite based on the properties of its constituents. The first micromechanical model used was the modified rule of mixture. This model considers a strengthening factor, which contemplates filler orientation and finite length and is best suited for particle composites. The second model used was the Halpin-Tsai model. This model considers shape fitting parameter, which contemplates shape and size of the filler into account. Through the results obtained through microindentation, you can also determine the hardness of the as-prepared composites, as is shown in the figure to your right. You can appreciate that the filler with the highest amount of reinforcement, 6% in mass, has a 6% increase of its hardness. Through dynamic mechanical analysis, the storage modules, as seen in figure A, and the loss modulus, as seen in figure B, can be obtained. It is observed that for the composite with the highest amount of reinforcement, which is corresponding to the 6% in mass of the ferrotitaniferous sands, increase in storage modulus of 5.3% and in loss modulus of 13%. Also through dynamic mechanical analysis, the tan delta curve can be obtained. As you can see, the glass transition temperature of the matrix was not affected by the incorporation of the ferrotitaniferous sands. Also, the damping factor of the matrix was practically unchanged after the addition of the filler. Through the results that were obtained, the following final remarks can be stated. The optimum contents of ferrotitaniferous sands of 6% in weight was defined by microindentation, since it allowed obtaining increases up to 6% for both Young's modulus and hardness. Both micromechanical models, the modified rule of mixture and the Halpin-Tsai models, supported the experimental results through their predictions of elastic modulus. Finally, through DMA, it was determined that the composite with the highest amount of reinforcement, the 6% in weight of the ferrotitaniferous sands, also exhibited the highest increase in storage modulus at room temperature and glass transition temperature at around 150 degrees Celsius. Besides, the tan delta for all composites was unchanged indicating that the vibration damping parameter was not affected by the reinforcements. Finally, I would like to give a special thanks to everyone that attended this presentation.